for giving me the opportunity to talk here. And also thank you for coming to this room, in this session. Well, I'm going to talk about a recent paper that came out like 2 weeks ago or 2.5 weeks ago. And it's about computing this, the first stringy corrections to some 5-point function of 20 prime operators in n equals 4 to 3 fields. So again, we are going back to this famous example of ADS-FT. And we'll be studying the strong coupling regime of n equals 4, where lambda tooth coupling is GN squared n, and it labels the SUN gauge group of n equals 4. And this, we know, it's dual to type 2B string theory on ADS5 cross S5. And then one natural thing is, okay, we started in the supergravity regime, we have some classical string theory interpretation in the ball, and now we'd like to compute some 1 over lambda corrections to this, which map on the gravity side to basically alpha prime corrections or higher derivative corrections to your supergravity action. And Francesco in the first week was also mentioning the 1 over n corrections to this kind of correlation functions, and these are related on the other side to bulk loop diagrams. Okay, so in this talk, our goal is to compute the first stringy correction to a 5-point function. So we'll be looking at here and keeping infinite n. And what is the object that we want actually to study? Okay, it's like this 5-point function of 5 20 prime operators. We just call it O2. And these guys, they are LPPS operators with protected scaling dimensions. We can suppress. They are in the protected scaling dimension equal to 2. That's why the 2 here. And these guys have some hard symmetry indices that go from 1 to 6. Okay, and we suppress them by introducing some null polarization factors, as Rodrigo was discussing before in the other context. And if I have TI, okay, so these are in the symmetric traces of presentation, well, that's enough for me. Okay, in particular, this O2 is dual to some scalar fields in ADS, and in particular is the lowest KK mode of this graviton reduction, and they are the bottom components of the stress tensor mode. Okay, so what do we know about these objects? Actually, this was first computed in the supergravity regime by Shinan, Vasco, and Raul Pereira in 2019, and then in 2023 there was another paper by the same authors and also myself and Carlo Meneghelli, where we compute the same 5-point function, but now with 2 extra, well, 3 O2s and 2 OPs for more ordinary KK modes. And last week, Bruno was telling about this recent program where we compute all the KK modes, basically. So this was work done by Vasco, Bruno, myself, Zongji, Ishao, and Eliziwan. Okay, like 2 weeks ago. Okay, but we know about this, how they behave in the supergravity regime, but we don't know how much we can say about stringy corrections. So my idea in this paper was, okay, we know the bootstrap conditions that we are always applying for these 5-point functions are basically always the same. We use some kind of properties of Mellin amplitudes, factorization, we use some ingredients from supersymmetry, and then we try to bootstrap what should be this an ansatz for this answer, and it seems to work. So it's you can say basically a naive estimate that in principle this should also work at the level of computing string interactions, and that's what I try to do. And actually, it almost fixes everything, but we'll see that there's very little that it remains to be fixed in the end. Okay, so Francesco, Bruno, and Alice already motivated why we need, and Chinan also motivated why we care about 5-point functions or higher point functions in general. But if you're not there, let me just give you very quickly some motivation why we care about these options. So why higher points? Okay, the first thing is that they contain much more OP data. Okay, inside a 5-point function, for instance, there's in principle infinitely many 4-point functions. So by studying a 5-point function, are you considering immediately all the CFD data that is contained in an infinite amount of 4-point functions? So if you know how to extract those 4-point functions or 3-point functions inside, then you are accessing. By studying one object, you are accessing much more information at a single time. In particular, in holographic theories, if you just want to study things for scalar operators like we are doing here, by just considering a 5-point function of scalar operators, you have access to OP coefficients involving 2 double traces and 1 scalar. This is something you would not see by just studying very generic 4-point functions or even infinite amount of 4-point functions of scalars. You wouldn't see this object. Okay, so this appears at 5 points. Other motivation is what Francesco discussed in the first week. These ADS unitarity methods allow you to construct CFT data at higher loops by knowing information from lower loops. In particular, the one loop case, you can build it from squaring the tree-level data of the CFT. But as you go for higher loops, for instance, in the 4-point function, the two loops, you should consider this cut, and you immediately see that this is basically result of gluing 2 5-point functions. So you need to consider these objects if you want to use these methods. Another thing is, okay, we know some relations and identities and even hidden symmetries for 4-point functions. Are these things only for 4-point functions? It's just a particular case of 4-point functions, or does those things survive for higher point functions? Well, based on the recent results, it seems, at least in ADS5 process 3 and ADS5 process 5, that hidden symmetry survives at 5 points. But you can ask, what about, how can we make seem to survive? But you can ask, how about, for instance, double copy that should be possible in reduced correlators for 4-point functions? Can we make these things precise for higher points? Are there any new relations that only become apparent once you go for higher multiplicities and you don't see at the level of 4 points? All these questions give us the motivation to study these objects. Okay, let's move on and start saying things about these objects, things that we know, apart from the supergravity regime, but very general statements about these guys. Okay, the first thing is that we introduced these polarization vectors, TIs, and these null polarization vectors just to suppress the R-symmetry dependence of these operators. So in the end, they have to appear in your correlation function just as monomials of this form, where these AIJs are symmetric. And they have to satisfy that once you sum over AIJs, they have to be equal to delta I, which in this case is always 2. So you can count how many structures you can write of this form, and basically they have to be of this type of structures. Either you have something which looks like a pentagon, or you have a triangle and then 2 outside. And if you count all of them, there are 22 R-symmetry structures. Okay, and here comes in some way, the difficulty of going for higher points is that once you start to go to higher points, you have many and many more R-symmetry structures. So any ansatz you make, then you multiply by 22, 27, so on, depends on your KK modes, becomes hard. But you can do it. More constraints that we know. Okay, this is basically the R symmetry that you can have, dependence. Then we know constraints from SUSE. Well, Rodrigo was telling us in the previous talk about superconformal word identities in the case of 4 points. And in that case, we know a lot. We can write this dynamical function, extract some reduced correlated from, basically that's the reduced correlated, just extract some R dependence in front that satisfies some kind of algebra constraint. Here, at the level of higher points, superconformal word identities were not systematically studied, but we know some constraints that we can impose. One is again chiral algebra, but this is a 2D constraint. Okay, so what's the difference between 5 points and 4 points? At 4 points, generic kinematics can always be mapped to lie in a single plane by some conformal transformation. So actually, people observe that just imposing chiral algebra basically knows about everything that you can impose from supersymmetry at level of 4 points. Nothing else is there. For 5 points, that's not the case, because if you have a generic kinematics in 5 points, it's not always the case that you can map it to a plane. So there's some information about the full kinematics of 5 points that you lose by just imposing chiral algebra. And let me perhaps say one way of writing this chiral algebra constraint is basically, okay, I didn't say, but these Tij's are Ti.Tj's. Is to choose this kinematic constraint where you put your 5 points in a plane labeled by Z and Z bar. And then you just choose something like this, where V and Vj are arbitrary. Okay. What this tells you, this chiral algebra constraint, is that your correlation function, but for generic, and actually, when you choose this Tij equal to that, this thing is only a function of Z. There's no dependence on Z bar, so it's only and the Tij's, sorry, and the V's. And in particular, it can be computed from free theory. Well, it depends if you do this one is actually Z bar, sorry. You can do the opposite. The other case is the other constraint we know is another choice of twist, which is not given by chiral algebra, so they are different. They give different constraints. It's a Drucker-like twist. There is a topological. It's topological in nature, and basically says that once you take Tij to be equal to Xij squared, your correlation function becomes topological. And it's just given by a constant. So again, you can compute it from free theory. Okay. So we have some constraints from supersymmetry. And now, what else can we say? How can we build these 5-point objects? The next step is the usual step we did for all these results in the supergravity regime, is to use Mellin space and then the simple analytic properties of Mellin space for all graphical range. The most relevant for us is Mellin factorization. Mellin amplitudes have poles, some location, determined by this, where tau is the twist, scaling dimension minus the spin of some primary operator, exchange primary operator. And 2m labels descendants. And then there is some function here, some residue, which is function of delta J's, of the Mellin variable delta J's. Okay. This delta, we know more about it actually. This delta L of R is basically some pole associated with some division of your Mellin amplitude into two, one left and right Mellin amplitude. Let's say we are doing some dividing our endpoint function in something that goes from 1 to k and from k plus 1 to n. Okay, these residues, okay, so first there's some pole here, I wrote there. And these residues were known by formulas found by Vasco, Knudonj, and Emilio. And these are basically giving some kind of gluing of right and left Mellin amplitude. So you are computing here just gluing together lower point functions. So for instance, in the case of 5-point functions, you always decompose in something which is a 3-point function, and then you glue it to a 4-point function. I mean, like this. Okay. This, to be completely concrete, this L of R is sum over A from 1 to k, B from k plus 1 to n, delta A. Okay, we know how the Mellin amplitude behaves at certain poles, and we know what are the residues. We can compute them by just gluing some lower point functions. So the idea now is, okay, if we know what are the possible exchanges, we know these lower point functions, we can glue them together and fix completely the singular behavior of the 5-point function. That's exactly what you'll do. We'll see that the 3-point functions we have to consider, or the poles, give you 3-point functions which are protected. And then the 4-point functions, we know what are the Stringy corrections. So if you glue this information together, we basically fix completely the singular behavior of the 5-point functions up to the order we want in the Stringy corrections. And we'll stop at first order, because that's already good enough for us.
So can I ask a basic question? So these Mellin amplitudes, they're always meromorphic,
yes,
yeah, and they can have additional polynomials.
Yes, you can have regular terms here. I'm just saying this is the behavior near
the
simple.
degree of these polynomials.
It depends on your flat space constraints. For the supergravity regime here, you could go up to could be linear, but you'll see in the next order R square you can have something more like S to the delta J to B. But I will come to this later.
The poles are always simple.
Yes. Here, yes. For 5-point functions, yes. Well, it's not really this simple because I'm okay. Let's be precise. Actually, it's can be you can have 2 poles, but it's not like a double pole, right?
Yeah.
A double pole would be if you go to position space, which corresponds to some logs, and those logs are corrections, anomalous dimension corrections. But of course, if you're gluing a 3-point function and a 4-point function, you have already a pole here. The 4-point function can now again have some poles, so you have
another part.
Yes. Okay, so what we need to know, what are the possible exchanges? Okay, one thing is that we don't need to care about higher traces because, as Rodrigo was saying, the gammas that appear in the definition of the Mellin amplitudes already take into account those contributions. So we can just focus on single traces. And in particular, we can focus on low twist single traces. Stringy states, their scaling dimension or their twist grows with lambda, and as we are taking lambda to go to infinity, actually they decouple from the theory. So we don't need to bother about them in these poles. And by just looking what are the non-extremal couplings and what are the allowed R-symmetry selection rules, R-symmetry selection rules. This is basically the same exercise you would do for the supergravity case. We see that the possible contributions appearing at these poles are again the O2, the R-symmetry current, and the stress test. Okay, so you need to know basically for fixing the 5-point function, the singular behavior of the 5-point function at a given order in the Stringy corrections, you need to know these 4-point functions. Well, X. where X is one of these guys. Okay, so this is very well known with the O2. These two were not known, but we can compute using some superspace computation. Okay, and we solve the first order and some of the example. Okay, so much time. Okay, I will run a little bit, so I will not give you more detail about this and just skip to the next step. So I think you can understand how exactly we would do it. Like you just write down an ansatz for your 5-point function, respecting this constraint. Basically, you want something which is some melon amplitude, delta j Tij, which for the connected part goes 1 over n cubed for the 5-point function. Then there's some Sugra behavior that was computed before. Then the first Stringy correction appears at order 1 over lambda to the 3/2 times something. I will label it like this. And we are just computing this function. And then, of course, more things. Okay, so you write down something. Now, because you have an 8th derivative theory, you can have the scaling growing like delta j to the 4th. In large delta j limit, it can grow like this. So you just write down an ansatz compatible with this singular behavior, with this the singular behavior fixed by this Mellin factorization properties, and then you have some regular terms that in the end you have 5 variables. You write all the polynomials up to this order. You multiply by 22 structures, and then you have an ansatz. Okay. So the singular behavior is determined by factorization properties of the Mellin amplitude. And now we need to fix basically what are the regular terms that the Mellin amplitude might also have. And for that,
sorry, this is not the same as like what people do in amplitudes like this CFW recursion.
This is very similar to those things, yes.
Except that you have additional terms, like polynomial terms.
Yes.
So it's a bit more.
So these factorization properties are very similar to flat space things that you can split an amplitude with some propagate in the middle and compute lower point functions or lower point amplitudes. That's one of the reasons why people want to use this Mellin amplitudes to study this scattering in the ball. Okay. Now, fixing regular terms of the ansatz. The Truga-Pletka twist, there's no constraint in the kinematics, so we can consider completely generic kinematics of the points x1 to x5, and can be imposed completely in Mellin space. Okay, so we don't need to do anything. We just stay in Mellin space. We take this special choice of polarization vector of the polarization vectors. Once we impose this, I don't know, okay, it's not there. So you're in our Mellin amplitude, the connected part of some endpoint function is given by some integral. Then you have your Mellin amplitude. Then there's, by definition, we have some dependence on gammas. 1 to n, Mij, Xij squared minus delta ij. Goes like this. So, and this dependence is basically just all the R-symmetry structures multiplying some function of delta ij's, what you would usually call your Mellin amplitude if you didn't have this R-symmetry. Okay, so you see if you just put Tij to equal to Xij squared, it's basically doing is like shifting the dependence on Xij. So you can always redefine what you mean by delta j. So go for delta j tilde, and then you shift back to this so that you have again the definition of what is the Mellin amplitude for you. This of course will shift your gamma functions, but also the dependence on the Mellin amplitude. But in the end, it's just a difference operator that Rodrigo was mentioning before, and you just have to do it for all of the R-symmetry structures. Let's say R-sim. There's some difference operator for each one of them, acting on your Mellin amplitude, And in the end, because your correlation function is just a constant, in Mellon space, the naive prescription is that it should be equal to 0. Okay, you do that, in the end, you have 20 coefficients of the regular terms to be determined still. So, okay, in the supergravity regime, actually, Drucker-Plewka was enough to completely fix the regular terms in terms of the singular terms, and everything was solved. As you go for stringy corrections, apparently it's not enough. So what you do next, okay, chiral algebra then. These are not the same constraint. So what you do, because chiral algebra is a two-dimensional kinematics constraint, you don't really know how to impose this in Mellon space, because, well, if you have a 5-point function, you start with 5 cross ratios, then you go to a two-dimensional thing. You don't have all the 5 cross ratios independent, so you are losing some independence on these xij's, and then of course on your cross ratios. So then of course it's not clear how to impose this constraint in Mellon space, but you can map your Mellon amplitude to position space using the fact that you can always write this Mellon amplitude in terms of some products of Pochhammer's or gamma functions, and write your ansatz as a linear combination of the functions. Okay, and these functions can be evaluated. They are complicated functions depending on the weights of your external operators and some shifts on these weights, but they can be evaluated. They are given as in terms of a basis of one loop scalar box diagrams and logs and rational terms. You can choose, now you go to the planar limit. Not all the integrals are independent, but you can select the basis of independent functions, and you control to take this choice of Tij's. And then in the end, you see that in order to have something that does not depend on Z, you cannot have this scalar box diagram surviving. So you just, for any V, you impose that the coefficients multiplying those integrals need to vanish. And you go down to 2 coefficients remaining. Okay, this is sad because this is like the rigorous approach that you would have from in a bootstrap perspective to completely fix everything in the stringy corrections. But in the end, there's still 2 coefficients left, and we don't know what else to impose. But then you look again and you say, okay, what are these 2 coefficients and what are they multiplying? And you see that actually these 2 coefficients always multiply things that go like delta j to the power 4. So they are basically giving you the high energy, they determine the high energy regime of the Mellon amplitude. And for 4-point functions, you would expect these things to be completely determined by flat space. So you think, okay, let's look, what is the 5-point function of 5 gravitons in 10D, compute the flat space limit, and then relate the 2 and fix what are these coefficients. There's a caveat on this. People are worrying about this at the moment, but for now, let me forget about the caveat and just present how it would go. So you can look at these works by Oliver Schlotterer, Karl Zumaffer, and many other, and they actually write what is this closed string amplitude for 5-point functions. Of course, something that I should write is the Panadonic formula for 5 points. It goes basically. Some alpha. Okay, this is like, yes, this is 5 usually. In this case, your Mellon variables, this is redefinition of your Mellon variables, this form. Sorry. and you take these guys to scale with L, which is the radius of ADS, and you equate them to the Mandelstam variables in flat space, and then there's still this dependence. So, okay, this is annoying. It's 15 halves here, but let's move on. This is the polarization tensor of the gravitons, and they can be built from the T's in this way, where you just had you go from the 6-dimensional vector to a 10-dimensional by adding zeros, and you see, of course, this remains like symmetric and traceless, as you would expect. And then you compare. So these guys computed how this 5-point closed string amplitude behaves, and you see that in the supergravity regime, it actually goes like order S, capital S, ij to the power 0. And then the alpha prime cube correction goes as it should, just like this. Okay, and this is actually the behavior that you see in the supergravity regime of your 5-point function in Mellin space. If you just do this. Okay, so you would expect from this naive scaling limit that also I should vanish. Can I vanish the coefficients that are order little s to the quotient? Yes, okay, and this completely fixes these two coefficients. I'm just saying, okay, the scaling, if I should have this, if the Mellin variables are related with the Mandelstam variables, then I should be able to have the same powers on both sides. I should have this, right? The sugra seems to work fine. And you expect the alpha prime corrections would go the same way. So you just impose that these guys vanish, and then everything is completely fixed. What's the caveat? The caveat is that this flat space limit formula actually works for a specific kinematic. So it's not the full amplitude that you get. You get the amplitude provided that all the polarizations are orthogonal to all momenta. So if you have 5 points, at some point, one of these guys will have to contract with some momentum. So actually what you get on the flat space is a 0. So you are comparing a 0 with something, and then you have to figure out how things can actually be equated one to the other. This goes like order s to the 0. There's some integral, some limit, and then you get to 0. Actually, it's the limit that is giving you the 0. So your Mellin amplitude is not computing a 0, it's giving you something else. But by comparing what is the dependence on the ADS radius on both sides, you see that your Mellin amplitude is actually computing suppressed corrections in 1/L. If you expect this to be a good interpretation, you would say, okay, I have some scaling. Actually, this is suppressed by L to the -9/2. Then you expect, okay, this is the sugra. This multiplies the sugra and gives me the 0. And what I'm saying next is that I shouldn't have something which scales, it's less suppressed compared to the flat space than the sugra. So in the flat space, you'll get another L to the 6. So I'm just saying, okay, L to the 6 comes with this Sij to the cube. I'm over time, so I'm rushing, so I'm not being very clear. So what I'm saying is that you get the 0 by having some suppression 1/L. And then the next order term should be also suppressed by the same guy, or they can never be less suppressed than the supergravity regime. By imposing this, then you fix these two coefficients. Why there's a point, why this is not super rigorous is because we are only trusting some formula that should work like case by case, clearly the same scaling dimensions on both sides, the same scaling in all the parameters in both sides, and it's not actually happening. So you can still get a 0 on this side by just having a higher power here of L, and this suppression will still guarantee. If you have like s to the quarter, s to the power 4, you would still guarantee the suppression in 1/L that would give you the 0 on the left-hand side. So my motivation to fix this to coefficient is that a good interpretation of your Mellin amplitude is that Okay, this is computing 1 over L corrections to the flat space limit formula. So it starts at order 0 with the same scaling that we observe in flat space, and higher orders will also be suppressed in the same way. And then I fix these coefficients. Okay. If you don't like this, because it's not super rigorous, I also give the result without imposing this constraint. Okay, so outlook very fast. One way to make this more precise, I believe, I'm not sure, but I would like to try, is to go for 6-point functions. For 6-point functions, we know that flat space limit has more information. There's no halves power here annoying you. So everything should match exactly on both sides. Actually, this has been done for gravitons and gluons by Vasco Aldai and Chinan and Maria. And the flat space has more information. So I would say that if you start the flat space limit of 6-point of this guy and you compute stringy corrections to this, the singular behavior of the dominating terms in the flat space limit formula are related with some 5-point function with 1 stress tensor and 4 O2s, and this can be related to the 5-point function of 5 O2s. So you can probably make these things more precise. Another thing that we can do is, if you want to generalize this for generic AK modes, is to avoid having chiral algebra being implemented in position space where you have to compute everything, all these diff functions, and these become complicated. So you'd like to have chiral algebra being implemented immediately in Mellin space. How to do it, I don't know. This would help generalize for generic AK modes. Okay. Other thing is, of course, there's alternatives to this, but in principle, you can go to higher orders in 1 over lambda because we have information for that from the 4-point functions. It's not clear how much we can actually fix by using the same strategy, but it's a good exercise to try. And then you can try to generalize these stories to other theories. And also extract OB data from this result. Okay, you have non-protected OB data inside this 5-point function, and we can try to actually look at this and extract this OB. And with that, let me finish, and I'm sorry for going over time.
This basic question, if you go to higher order in 1 over lambda, you get higher powers of these structures, but then presumably you're going to get way more.
Yeah, it becomes harder to do just because of this thing of having larger ansatz, and you have to fix it. Actually, it's not that hard to fix completely the factorization part. So that's not super annoying. The singular behavior. The most annoying part is imposing chiral algebra, because you have to compute these diff functions, which the complexity grows in with the KK modes. So you would like to avoid doing this for those cases, and of course the ansatz grows, but it's not impossible to do. Well, if you want to go to any order, then I would say it becomes more and more non-trivial, but in principle you can do it.
Guys, did you know at what order or what derivative order there's the first fully contact interaction?
For the 5 points. In EDS, I think
Something with an article fifth.
yeah.
But it's not without derivative.
Yes. But there's some very recent paper on doing this for flat space, not the ES flat space. I need to move. I can tell.
Did I understand correctly that from the 5-point function of O2, you can't learn anything about the flat space amplitude? So suppose you knew the 5-point function of O2.
Yes. So
Because of the kinematics, you can't learn anything about
because of this thing of having always one momentum contracting this polarization vectors that gives you a 0, you would be saying you don't learn about the flat space, you learn about something which is 1 over L. which is a bit annoying, but 6 points in principle works fine. Actually, I know that works fine because the supergravity regime has been computed by other methods and then compared to 6-point amplitudes in flat space, and then they agree precise.
More questions or what would be? Guess next one again.